Now, this particular system here is 40 petaflops, which is approximately the performance of the Sierra supercomputer in 2018. The Sierra supercomputer has 18,000 GPUs, Volta GPUs. This one node here replaces that entire supercomputer.
Computing is approaching a hard limit. Even the most powerful GPUs are struggling with problems that grow faster than machines can handle. NVIDIA believes the solution is not faster chips, but a new kind of computing, where AI, GPUs, and quantum machines work together as one system. NVIDIA's roadmap to the quantum era. For years, quantum computing was presented as a replacement for classical computers. NVIDIA rejects this idea entirely. Instead of betting on quantum machines alone, it is building a roadmap where quantum systems become part of a much larger accelerated computing ecosystem. NVIDIA is not trying to build quantum hardware or qubits, nor is it competing to create the most powerful quantum processor. Its strategy is far more practical. The company is focused on turning fragile, experimental quantum devices into tools that scientists can actually use in real workflows. At the core of this strategy is a simple reality. Quantum processors cannot operate on their own. They depend heavily on classical computing for control, error correction, simulation, and optimization. Without massive support from CPUs and GPUs, quantum machines remain confined to laboratories. This is why NVIDIA's roadmap centers on infrastructure rather than hardware ownership. By integrating quantum processors into existing supercomputing environments, already powered by GPUs and AI, NVIDIA enables quantum computing to evolve gradually. Instead of replacing classical systems, quantum machines enhance what already exists, creating a transition path rather than a technological reset. Quantum accelerators, not quantum replacements. A common misconception is that quantum computers will eventually speed up every type of computation. NVIDIA's strategy is built on the opposite assumption. Quantum processors are extremely powerful, but only for very specific kinds of problems. Quantum accelerators are not designed to replace classical computers. They function like specialized engines, handling tasks that classical systems struggle with, such as simulating quantum systems, solving complex optimization problems, or sampling high-dimensional probability distributions. In a quantum-accelerated workflow, classical systems still do most of the work. CPUs manage orchestration and control. GPUs handle AI, simulations, and large-scale parallel processing. Only carefully selected portions of a problem are sent to the quantum processor. This division of labor is essential because quantum machines have fundamental limitations. Information can only be extracted through probabilistic measurements. Qubits are fragile, unstable, and highly error-prone. Running a single quantum algorithm requires extensive classical computation before, during, and after execution. Quantum acceleration works because it accepts these constraints instead of ignoring them. Classical systems prepare data, optimize quantum circuits, manage control hardware, and process results. The quantum processor does only what it is uniquely suited for, nothing more. By treating quantum processors as accelerators rather than replacements, NVIDIA avoids the biggest trap in quantum computing. This model allows practical progress today, even as quantum hardware continues to mature slowly. GPU-QPU hybrid supercomputers. The real breakthrough in NVIDIA's strategy is the rise of hybrid supercomputers, systems where GPUs and quantum processors operate as tightly coupled parts of a single architecture. In this design, the quantum processor is not an external add-on. It is deeply integrated into the computing stack. GPUs handle tasks that quantum systems cannot perform on their own, particularly real-time error correction, large-scale simulation, and AI-driven optimization. Quantum error correction highlights why this integration is critical. Correcting qubit errors requires constant monitoring, rapid computation, and immediate feedback, often thousands of times per second. Without GPUs performing these calculations in real time, quantum algorithms would collapse before producing useful results. This tight coupling also enables large-scale quantum simulation. Before algorithms ever run on physical quantum hardware, GPUs simulate quantum systems at the edge of what classical computing can handle. These simulations allow researchers to test ideas that today's quantum machines are still too noisy or limited to support. In hybrid systems, GPUs become the stabilizing force that makes quantum computing usable. They turn fragile experiments into scalable workflows and allow quantum processors to grow without collapsing under their own complexity. This is why NVIDIA sees the future of computing as hybrid. Not classical versus quantum, but classical and quantum fused into a single accelerated platform. Where this changes the real world. Hybrid quantum computing is not about abstract speed. Its real value emerges in problems that grow too complex for classical machines to manage, no matter how powerful GPUs become. In drug discovery, researchers simulate molecular interactions involving countless quantum effects. Classical systems rely on approximations that introduce significant error. Quantum accelerators enable more accurate modeling, while GPUs handle pre-processing, optimization, and AI-driven analysis. This could compress drug development timelines from years to months. Climate modeling faces similar limits. Weather systems are chaotic, multi-scale, and highly sensitive to small changes. Hybrid supercomputers combine classical simulations with quantum-enhanced calculations to explore climate scenarios that were previously unreachable. Better modeling leads not just to better forecasts, but better decisions. Optimization problems form another major frontier. Logistics networks, power grids, traffic systems, and financial portfolios all involve explosive combinations of possible states. Classical algorithms struggle as these systems scale. Quantum accelerators open new paths through these solution spaces, guided by GPUs and AI. Even AI itself stands to benefit. Training large models is increasingly constrained by cost, energy, and time. Quantum-enhanced sampling and optimization could unlock new training approaches, while GPUs continue to handle the bulk of computation. The result is not simply faster AI, but AI capable of exploring solutions classical systems cannot reach. Why NVIDIA has the advantage. Many companies are racing toward quantum computing, but most are focused on building standalone quantum processors. NVIDIA's advantage comes from choosing a fundamentally different battlefield. Rather than competing on qubit counts or hardware novelty, NVIDIA focuses on integration. It already dominates accelerated computing, AI infrastructure, and supercomputing workflows. In NVIDIA's vision, quantum processors plug into an ecosystem that already exists. This matters because industries are not ready to abandon classical computing. Most organizations cannot wait for fully fault-tolerant quantum machines to arrive. NVIDIA's hybrid approach allows them to adopt quantum computing incrementally, using it where it works today, and expanding as hardware improves. Software is another decisive advantage. Hardware alone does not create a computing revolution. GPUs transformed supercomputing only because they were supported by mature tools, libraries, and developer ecosystems. NVIDIA is applying the same lesson to quantum computing, enabling scientists and engineers to work in familiar environments. This lowers the barrier to entry. Instead of requiring quantum specialists, hybrid systems allow domain experts to use quantum acceleration without rewriting their workflows. While others chase quantum supremacy, NVIDIA is building quantum usability, and history shows usability wins. The shape of the computing future. Quantum computing will not arrive as a single dramatic moment. It will emerge quietly, integrated into systems that already power science, industry, and AI. Future supercomputers will not be defined by one processor type. They will act as orchestration engines, directing CPUs, GPUs, and quantum processors to work together on the same problem, each handling what it does best. Some tasks will never touch a quantum processor. Others will rely on it entirely. Most will move fluidly between classical and quantum stages, guided by AI systems that decide where computation should happen. This is the future NVIDIA is building toward, not a replacement for computing as we know it, but an expansion of what computing can do. From experiment to infrastructure. For decades, quantum computing existed in isolation. Fragile machines, controlled environments, and experiments that proved theory but delivered little practical value. The missing piece was never quantum power alone. It was everything surrounding it. By treating quantum processors as components inside a larger accelerated system, NVIDIA shifts quantum computing from experimentation to infrastructure. In this model, quantum machines no longer need to be perfect to be useful. Their weaknesses are absorbed by GPUs, AI systems, and classical control layers. Errors are detected and corrected in real time. Algorithms are optimized before they reach quantum hardware. Results are refined through accelerated post-processing. This is how technologies scale, not by waiting for perfection, but by engineering systems that work with reality as it is. The same transition happened with GPUs, and quantum computing is now at the same threshold. What changing computing forever really means. This transformation is often misunderstood as a race for speed, faster answers, bigger numbers, more power. But the real shift is deeper than performance. Hybrid quantum systems change which questions can be asked. Problems once dismissed as too complex, too uncertain, or too computationally expensive become approachable, not because they are solved instantly, but because they can finally be explored meaningfully. Scientists test ideas instead of approximating them. AI systems search solution spaces that were previously unreachable. Industries optimize systems once guided by rough estimates and intuition. Computing stops being a rigid pipeline and becomes an adaptive intelligence, one that decides how to think before it decides how fast to think. The quiet beginning of a new era. There will be no single moment when quantum computing arrives. No switch will flip. No headline will mark the transition. Instead, quantum acceleration will quietly integrate into data centers, research labs, and AI systems. At first, it will assist. Then, it will enhance. Eventually, it will redefine expectations. NVIDIA's approach ensures that when this happens, the world will already be ready. The tools will exist. The workflows will be familiar. The bridge between classical and quantum will already be built. This is why this moment matters, not because a quantum chip exists, but because computing itself is being redesigned to include entirely new ways of thinking. And once that happens, there is no going back. If this future excites you, like the video, share it, and subscribe for more deep dives into the technologies reshaping our world.